The instructor forgot to turn his microphone on. So this is being dubbed real time. Today we'll talk about a subject that's immensely important in all of physics and also in nonlinear dynamics, subject of symmetries. We'll do this in two stages. First we'll discuss, I don't know what he's saying, but anyway. First we'll discuss discrete symmetries, which are rather simple and quite intuitive. And a week later we will start discussing continuous symmetries and their implications. That turns out to be somewhat more difficult. Discrete symmetries are extremely intuitive, and we'll illustrate them by the three-disk pinball. So there are three circular disks of same radius in the plane placed at the tips of equilateral triangle, and we'll label them arbitrarily 1, 2, 3. We will assume a free motion of a particle, high degree of symmetry. The system is symmetric under flip by any of the three symmetry axes. The group has many names. It can be called a permutation group on three symbols, or S3. For our physics application, it's actually better to use a more geometrical description. From the 19th century crystallography, we have inherited a couple weird names. They're called dihedral groups, or in some sense more natural and convenient for me is the notation S3V. The lecture is explaining that one of the symmetries is now rotational symmetry. That part is called cyclic group in three symbols, but combined with flips, it's called C3V, in which V, for some mysterious reason, refers to symmetry. And writing group elements in this way is most intuitive. This group is actually good enough to explain almost anything about discrete symmetries because it's a non-abelian group. Possible distinct symmetry operations. Their number is 6. That's called order of the group, and we'll denote order by putting in between vertical brackets. The group has rotations, has identity, rotation by 1/3, rotation by 2/3, a flip around the axis, and the flip around two other axes. First you rotate by flip. Altogether 6 elements, and they close a group. Any product of the two is an element of group. So let's remember what is the definition of a group. Group consists of some number of abstract elements. It always contains identity. And the group can be finite, so maybe it has n elements, or it can be an infinite group. Continuous groups, for example, will have infinitely many elements. If the number of elements is finite, we can talk about the order of the group. And what defines group is the operation of group multiplication, which we can denote in a few ways. We can use a little circle to be a symbol for group multiplication, meaning we apply one symmetry operation and then we follow it by another symmetry operation. Or we can just write G2 multiplying G1 because the convention is always we operate from the left. So the first one, then the second one. The group satisfies 4 properties. It's closure, so product of 2 elements is element of the group. Associativity, the order in which multiplications are performed doesn't matter. This, for example, would not be true if this group had to do with octonian matrices, but we won't consider that. It always has an identity, and it always has an inverse, meaning for every element of the group there is another group element and only one, product of the two being in either order being the identity.